there are less student or no student installed, there's no point for me wasting my time here, right? Okay, because you see, we got 150 students, right? I really don't want to waste my time on just few students. Because I'm not liable to teach you all this. It's your assignment, okay? You see, I'm trying to be very hardworking lecturer, and you guys don't hardworking, you know, how things going to work out. Okay, maybe I will do it in the next class. So you guys got, you know, times to do your installation. All right. So maybe that you all can see the difference between Plex and Simulink for this round. All right. Okay. So let me start our. Okay, DC converter. Okay, we are done. DC AC. I mean, basic lah is done. Those advanced one like space vector modulation, you know, multi-layer inverter. Okay. Well, we really have no time to go for it already. Okay, but however, whatever I teach in that DC AC is good enough for you to work in industry as the, you know, expert already. Okay, all right. So now we have to move on to DC converter. Because DC, AC, and DC are the most important so far for this what we call this current trend of applications. All right. Wait, how come the full screen thing come over here? Wait, something is wrong. Maybe I need to share screen at a different screen. Okay. Okay. All right. So DC converter. Okay, like the name imply, right? You are converting a DC input voltage or current into a DC output voltage and current. Now, as we know that DC, there is no frequencies. Okay, not like AC, right? AC, we change the frequency for the sake of, you know, controlling the motor speed. Okay, and we change the magnitude, okay, for the sake of controlling the motor torque, okay, or the magnitude and the phase for grid connected purposes. So for DC-DC converter, it become, in fact, it's much more simpler, okay, and then because you basically just converting its magnitude. All right, its magnitude. So it's either stepping up or stepping down the voltage. Okay, and of course the other thing is that DC, right? We have polarity, the plus and minus. You can change the polarity as well. All right. So and then we will have this unidirectional and bidirectional as well. Okay, unidirectional one direction, bidirectional two direction. And then it also have its purpose, you know, if you're using to control DC motor, so you can control the accelerations, control speed. It gives also very high efficiency and also fast dynamic, okay, response. And the DC-DC converter are actually integral parts of the energy conversion. Okay, like for example, what we have learned is the DC-AC inverter. In fact, most of the inverter out there, right, is a combination of DC and DC-AC. The DC side is to convert your panel voltage, because our panel voltage and current actually change, right, when the sun irradiance changes. So the DC will just to make sure that whatever you change, your output remain constant. You know, the 400 watt DC there has to be constant for the DC-AC, so that you can actually inject the power to the grid, okay, in a much more steady manner. And similarly, it will also use in wind turbine system, okay, the wind energy, where your wind also change, right? So you will have actually fluctuations. So it also serves these purposes. Okay, one of the what we call classical DC-DC converter in the old days is what we call a linear regulator, which is our power supply. Okay, you can get this thing at Shopee. So it comes in the form of this is the IC not MOSFET or IGBT. Okay, 7085, meaning that okay, your input here, let's say is 12 watt, it will regulate for you output to 5 watt, regardless the change of your load. It will always give you 5 watt. So this is one of the typical application of a DC-DC converter. And also here you can increase up to 30 watt. Okay, here will still give you 5 watt. All right. Now the problem with this type of regulator is that if you look into Simulink, okay, Simulink will actually have this model. They actually control in a very linear manner. Okay, it is actually controlled in a very linear manner in the way that their efficiency, okay, you can see that it's very low. Now, still remember the efficiency. This is the input power. This is your input power, right? Okay, the current and wattage, okay, from the input, the current and wattage, and also the current and wattage at the output. Okay, which is here, the output. So you use the output to divide it by the input, you will get the efficiency. And what you get is the efficiency is only 51%. Very low, okay? 51% of efficiency. So where are the rest of the 49% of energy go? The 49 of the energy go into this transistor, the NPN transistor, that dissipate as heat. So you will find that this kind of regulator, right, it will also produce heat. Okay, the higher the efficiency, the lower the heat. The lower the efficiency, because these are the energy, right, 100%. Okay, of course you cannot achieve 100 in theory, in practice, but still, you still have 49% of power or energy that you are not used, you're wasted, That means you still take that much of energy here. 49% wasted, only 51% you use for your load. So that is the problem of this. We still use it today. Many products you open up, they are regulated here. Okay, we still use it. All right. So it's very inefficient. Why we still use it? It is simple. Okay, and then of course for low power it's okay, right? It's only 1 watt. Okay, you lose 0.49 watt, so it's considered low lah. So of course, if your load is 1000 watt and you lose 490 watt, that is a big amount of power, right? 490, you can power a lot of things already, right? You can power rice cooker, you can power even your microwave, all these big things. Okay, that's why it's still used, because mostly on very small power application. All right. So now, in order to say power electronic, we're dealing with something high power, like for example, PV. Okay, our PV easily, right, in a string, you get 1000 watt. Okay, or up to 10,000 kilowatt of a string. Then imagine if you lost 49%, you buy 10 panel, you only use 5 panel power. So it's really not economy lah. So with that, okay, the DC-DC converter come into play. So the basic idea of a DC-DC, okay, inverter begin with the idea of DC chopper. DC chopper work in this way. You have a 12 watt, you go through a MOSFET, connect to a load, and then you pulse them. And you pulse them 50%, okay, at certain frequency, you can see that you actually controlling the voltage to 12 watt to 4.9 or 5 watt lah. Okay, watt here. Okay, with a higher efficiency. Then if you want to increase the wattage, right, you just increase the duty cycle. Okay, let's say make it higher duty cycle, then you can control the voltage. It's variable. Okay, you can control voltage. All right. So this is the basic idea of a DC converter. So in the old days, okay, I mean we still call it chopper lah, because you are chopping the output, right? 12 watt, right, into this, and you take the average. So your multimeter measure, you will get like 4.9. Okay, I think we will skip this one. Okay, not enough time already for you all to do this. Okay, you can do it at home anyway. Okay, now we will come to DC converter. What we call these are types. Okay, like I said, a lot of type. I cannot go through every single one of them, but I will go through those important ones. Okay, the 4 most important ones, in fact 3 lah, the important ones here. It's buck converter, boost converter, and buck boost converter. I added one more flyback converter. Okay, that is because a lot of our phone charger nowadays are based on this flyback converter. Okay, our so-called fast charger, you know, 1 hour from 0% to 80% is all based on this flyback. That's why I decided to add this in. Okay, in the old days, I just talked about these 3. Okay, of course, other than that, we also have like separate, okay, chuck converter. We got half bridge bidirectional, okay, double active bridge converters. Okay, so these are just for your informations. Okay, now we start with the buck converter. Okay, the buck converter, okay, is used to step down the input voltage. Okay, remember buck is to step down. Okay, so a typical example, you know, it's just like a regulator. You got 12 watt in, you can get 5 watt or 3 watt. It's just to step down. So when you step down, okay, because this buck converter have a higher efficiency, which is greater than around 90%. So what you get is that your current can be actually higher than the source current. Okay, so you can actually increase your load current because of high efficiency. So this is the advantage of the buck converter. And then the DIDT, which is the change of the current, is limited by the inductor you use. Usually we don't really look into this because unless your load is very dynamic load, that means your load changes very fast. Okay, less than 1 second it changes. Usually DC load, they don't really change that much. Okay, so that the IDT doesn't really matter. Okay, now we look at the buck topology. So this is how the buck converter looks like. It will have a serial, okay, chopper. It's just like a chopper, like I said just now. And then you have a diode, have an inductor, have a capacitor, and this is your load. Okay, this is your load. Now you look carefully, this L and C is just like, it's actually the LC filter. It acts as a LC filter. Okay, but this LC filter is not to filter to produce a sine wave. Okay, but is to smooth out the switching frequency here. Okay, because the switching here, right, it had a very high frequency. So when you have a DC like this chopper, right, because there is no filter, you see, so you end up with this one. Okay, you end up with this what we call this, you know, what we call chop lah. But you know, in DC you should have a straight line, right? So this filter will actually help to smooth it out. It's a bit lag here. Then of course my videos. Okay. Oh, okay. So the buck converter topologies, L and C. Okay, it got 2 states of operation. The first state is when the transistor is turned on. Transistor turned on, what happened? This current flow in, flow through the inductor, charge the capacitor, and come back. the diode is in reverse bias. Okay, and then what happened is that you will see you are chopping it, right? You have positive, and then your inductor is charging. Your inductor is charging. Okay, and then where your transistor is off, the energy in the inductor, you see, plus minus, right? Charging. Discharge, it change to opposite direction. So it starts to discharge. So you can see the energy now discharge. And the process repeat again like that. Okay, in the next cycle. Okay, so that will give you a continuous current. Okay, that is supply, okay, to the load. Okay, continuous current that is supply to the load. All right. So it's just as simple as that. Two state on it, on and off. Okay, but what your load see will be a very nice, smooth DC. Okay, any questions? No, right? Okay. All right, so come to design. Now, if I want you to design a buck converter, my input is 12 watt, my output is 5 watt. My load is 1 amp. So to calculate the duty cycle, it will be D equals to V out over V in. That will give me 0.41, which is 41% of your duty cycle. And then how to calculate the inductor and the capacitor for smoothing. Now, let's say our frequency is 20 kilohertz. Now, usually for DC-DC converter, right, the frequency is pretty high. It can go up to even 100 kilohertz, depend on the power. The smaller the power, the higher the frequency. Remember, switching frequency, higher switching will have higher loss. But smaller power, the loss becomes so small. It's okay. But for high power, okay, the switching frequency are usually, okay, a bit lower. So your IL, the change of the ripple, usually can be go up to as high as 40%. And your delta BC, which is 2%. This one has to be very low, less than 10%, because otherwise your DC will become like very fluctuating. Okay, so let's say I already work it out. You will get this number. You will get this number. These are the two values. All right. Of course, if I change the spec, this one will change accordingly. Okay. Now, straight away, we come to MATLAB already. So these are the MATLAB, okay, you will need to create. Okay, so most of the thing you already know. Okay, and then this one maybe a bit new to you. Okay, this is the duty cycle PWM. Okay, the rest is the wattage, current, and okay, maybe I will just show you. Okay. Okay. Okay, this one is the PWM. You see, I put 42% because there are losses. Okay, this one is again in Simscape. Electrical is under control, not control. Power electronics, under power electronics control. PWM generator, DC to DC. Okay, take this out here. Okay, and then you just set the frequency, that's all. You just set like 20 kilohertz, right? The input is your duty cycle. Okay, so these are the value. Okay, we do the calculation just now. If everything works fine, you run at 0.002 seconds. Okay, because very high frequency. So you can see now our output is around 4.5, not 5 watt. Okay, our calculate will say 5 watt. Remember, they are turn on resistance, all that causing the error, not error lah, the deviation. Okay, but the thing is that you have to look at the waveform. Okay, so this will be the DC waveform. Okay, it will still have a little bit of ripple because we set only 2%. If you set lower, then it will be lower. Okay, and then here is the current. You will see the current. Okay, the inductor current. This is inductor current. This is your chopping. All right. Okay. So now what I want you all to do is that create this one. Try to change this one to get 5 watt. For example, if I change 0.45 here lah. Okay, and you run. You will see the wattage become higher, 4.9 already. See? Okay. Now try to do this one because later it's important because when we come to PI control, you need this model. Okay, you need this model. Okay. So try to do this now. Okay, maybe we have a break of around 10 minutes. I need to go out for a while. I hope by the time I come back, you already show some of your work here. Okay or not? Hello? Yeah.
Can. Okay.
Okay.
Yes, sir.
All right. Okay, let's see. Oh, no one is doing it. Oh, sama. Okay, Muhammad, Jim. Oh, very good. Oh, you tune until 5 volt. Okay. Okay, that's why you can see the theoretical calculation does not take into account of the voltage drop across the turn-on resistance as well as the voltage drop across the diode. Okay, normal diode will have like 0.7 volt, right? Remember, okay, if you want to increase efficiency, okay, and reduce the voltage drop, you may need to consider using the Schottky diode. Okay, Schottky diode will have a very low, like 0.2, okay, of voltage drop. Okay, so that will actually help to improve the efficiency. Wow, the 100 volt. Okay, your DC source has to be 12 volt in order to get it right. Okay, you may, okay, some of you here may not get the voltage you want. Okay, it could be because of the, the time of simulation is too short for you. 0.5? Juan, how come? Your DC voltage must be 12 volt. I think you are putting in 1 volt. You have to change the DC voltage, the input. Remember, the objective of the example is that your input is 12 volt. Your display cannot work. How come? Futu now you show display but it's just like not looking right lah. Okay, now if you look at my one, okay, the input is 12 volt. Okay, the rest I don't change anything. I just put diode. I don't change, the 4 voltage. I don't change. This one I just put. I also don't change anything. Okay. So inductor value should be the same as shown in the slide. Okay, 325 microhenry. Capacitor 25 microfarad. And then 5 ohm resistor because you want to have 1 amp, 5 volt, 5 ohm, you get 1 amp. Yeah, it's just like that, nothing much. Okay, if you follow exactly, you should be able to get the similar waveform. Now the time has to be very small, 0.002, because running at 20 kilohertz. Your time too high, you won't be able to see all this detail. Okay, you won't be able to see this detail. And you back to the slide. Okay, so now you can actually look at the waveform and you can actually do a measurement. Okay, a measurement of this, okay, by playing around with the what we call the scope here. Okay, and then you can actually click this one. And it will show you the scope. Of course, you can make it full screen. Okay, then you can actually move, the scope around. For example, maybe on the more stable side. Okay, you can have this point, and you can see these are the time, and these are the magnitude, and you can actually move this one. Okay, You can move around here. So you can actually measure the magnitude, okay, of this ripple current, okay, 1.2, all right, to here is 1.2. The lowest will be roughly around 0.8 lah, okay, roughly lah, 1.2, 0.8, okay. So the difference is 0.4, right? Okay, which is around 40%, okay. So the 0.4 is actually fit with what we see in the design criteria, okay, in the design criteria. So you can see the Y here, okay, the Y is around 470 milliamp, okay. So the 2 point here, the 2 point. So you go back to the equation, you can see this is the, the delta IL will be 40%, all right. So delta IL 40%, okay, it's actually 0.47. So you can actually, do the measurement here. I think we need to change to this point. How to do it? Wait, okay. We have to change to not the gain. Let's see, we converter. Okay. So you look at here, now we are measuring the one, with the cursor here. Okay, we move, okay, this is the lowest side if you want to get it accurate, and then this is the highest point, right? And you look at here, delta Y, so it's around 0.48. Okay, so that tell you the difference. Okay, the magnitude. See, when I move down, okay, it become like almost, the same with the previous one, then it will get a resultant of 0. Okay, so you can measure the height in between these two. So it should be approximately, okay, fit with your theoretical design calculation of 40%. Now, similarly, okay, if you look at the output voltage, okay, and you look at the point, so it should be again approximately 2% here. If I close this one. Okay, this is the voltage output scope. Okay, click this one for measurement. Okay, and of course you can zoom in if you want. Okay, let's say you just move it to here, more steady state. Okay, then you can just try to take the lowest and around the highest. Okay, so you'll be around 0.11. Okay, it's less than 2%. Okay, less than 2% of the ripple. If you look at the voltage here, you see it's around near 5 watt. Okay, on the so-called the positives, and the negative side will be right near 4.8. So these are the ripple. Okay, and this ripple cannot be avoided. Okay, it will be here. The only thing what we can do is that we only can reduce the magnitude. Okay, reduce the magnitude. Okay, by maybe changing the design, changing the filter design. Okay, maybe you want it to be less than 1% here, or or less than 1%. Then you may need to have a higher capacitor value. It will lead to a higher capacitor value. Okay, So it's quite normal, not to worry. Okay, then you will give a much more smoother DC output. Okay. So that is the basic idea of the buck converter design. Okay, you change the duty cycle. You set your, of course, you can set this one lower 20% also can. Already it's just example lah. So when you set it 20%, this one will become much more smoother because here it becomes more smoother already. Okay, or you increase the switching frequency also, you can actually make this one also much more smoother as well. Okay, you can actually make it much more smoother. So this just to show you that when you design a buck converters, okay, the capacitor and inductor are actually key. Okay, very important parameter for you to get a very good output. And of course, switching frequency is another factors. So this example, I'm using 20 kilohertz, all right? And then when we look at the efficiency, so it's the same thing. What I did is that I just measure the input voltage and current, okay, and then, output, then you will see that in this example, okay, similarly, the same design, right? We will have an efficiency of 89%. Just by using this switching only, So this is how the DC-DC converter come into play. Okay, I show you just now, when we use a normal linear regulator you bought from the shop, 7-8, the efficiency is, it's only 51%. But now this one, just a simple design, you can go up to 89%, okay, of efficiency. So you can see by just simple changing of this, you can actually add it now. Remember the average wattage here block, right? It has to be your switching frequency. You cannot put like 50 hertz. Okay, like this one, the average, the mean. You have to put 20. It depends on your switching frequency. Your switching frequency 20 kilohertz, you put 20 kilohertz, so that it will give you a correct output. So you can actually do it now by add another this, then you can actually measure the efficiency of this buck converter. The equation is here. Power or output divided by power input multiplied by 1,000 at 100%. That will be your efficiency of this, what we call the DC-DC converter. It's the same for your DC-AC, right? You measure the power input and the power output, then you get the efficiency of your DC-AC. And you will know the power loss, right? So here you can see we got 89%. That means there are 11% of power losses. So very obvious. The power losses is because of the voltage drop here. Okay, and of course the what we call turn-on resistance. So you have to choose. Sometimes same circuit, you choose to use Schottky diode. You can try when you have this one. You change this to a lower switching voltage. For example, from, okay, let's see, I got this model with me or not. Okay, let me check my MATLAB. Efficiency, wait. Sometimes I don't save all this. I will do only this buck converter, this detail for you all. The rest is the same when you apply to boost converter and buck boost. Okay, here. Okay, so, okay, let me just try to run this one. It's the same. I just add a voltage current. Then you will 80 something. So let's say I change this forward voltage to 0.2. As we know that only Schottky diode allow you to do that, right? You see, immediately, my efficiency go up to 94%. And I just change the diode. I don't change the circuit. I don't change the switching frequency. I just use the so-called correct diode. Then your efficiency shoot up to 94. And of course, Similarly, our MOSFET, right, got the RTS. This one is how many ohm? 0.01, 1, 2, 3, 10 milliohm. Maybe you get another one with slightly, lower milliohm. This one doesn't really affect much. Okay. Oh, this one we also need to change the frequency. Okay. So this one doesn't affect much, but this diode play a very important role here. Okay. So like I said, Schottky diode is actually, I would say the price actually almost no different, with the normal diode. Okay. So it's around like, if I'm not mistaken, it's like 50 cents. You get in Jalan Pasar. Okay. So like I say, that's why in the power electronic devices class, I stress so much on the, these component. Okay, we reverse recovery or all this. Of course, here we don't see the problem with the recovery, but we will see that, okay, it does give you a very significant efficiency, okay, compared to the linear regulator, right? So this is the, again, as I said, the reason why we need to use this switching frequency, because linear regulator does not have any switching frequency. It's fixed DC. Okay, so the advantage of, okay, using a buck, this is the buck topology. Okay, so any questions? Hello?
Yes, Dr. Rodney, I do have a question. I set the mean block, like you said, to 20,000 hertz, 20 kilohertz. But all of a sudden, my efficiency is none.
Oh, something wrong with your connection, no? Because what I did here is, what you see, what you get, right? I didn't hide anything. See, whatever.
That's kind of what I think also. Perhaps you could point out to me my mistake here. I just posted.
Oh, sorry, I don't do troubleshooting.
No.
Okay, so this is what I did here. Okay, you see all 20, 20, 20. Okay, first thing is that, Ryan, you have to make sure before you have calculation all this, right? You have to make sure the original one is correct first. The one without the efficiency one. You have to make sure it is correct first. Then only slowly you add it. You suddenly come here, if one of the part wrong, right, you may be getting into trouble. All right.
I did the other one fine, and the graph for that one was right, exactly like it came out. Only this one, when you got the efficiency inside, somehow it's not calculating.
Then you have to see because it's a very straightforward calculation. It's a very straightforward calculation to see. I'm not sure which part, because like I say, if I troubleshoot for you, it will take us some time.
Yeah, I know. I tried again, not infinite.
No problem. We'll see how about the rest in the class are they doing it. That's why it's very important that our class student take part in this exercise, because they will indirectly help you. Okay, if they can work, you cannot work, Ryan. You can talk to them why you can work. You see, that is my purpose, is to learn from each other. It's not a one way of communication. Everything got problem must be Dr. Rodney. Okay, everything got problem, I'm the one who solve. No, right?
No doubt. I'm just waiting for a second model to come up.
Yeah. See, where I mean, the rest are still on the original model. Never mind. Let's see who else have done this. Okay. Okay. I want you all to familiar with this one, because I will take this as the base model for do PI tuning and also for the Plex also. I will just show you how to do this simple one in Plex as well. Okay. Because I really worry not enough time. So I will go a bit quickly now, a bit fast. I will skip those. I think it's simple enough. No need to waste time. Okay, but this one is important for you as a start of a DC-DC converter. Okay, Ryan, yours on here. It's not calculating. You got infinity, right? Wow.
Infinity the first time, the second time 82 something. 82%.
Something is wrong. Something is very wrong. You see, your current here is 5 amp. Your R resistor, is it 5 ohm?
Resistor 1 ohm.
Wrong already. It has to be 5 ohm. 5 ohm got 1 amp. You see, You have to look at
Yeah.
my question carefully. Okay, Tê Bun Hong. We are dealing with 1 amp, 5 watt of power lah. This is a very, very old charger. Okay, are using this method. Okay, Ko Sing Yi. You see Ko Sing Yi get it right. 89. Yeah. So just now I just demo. You use the Schottky diode, you can increase the efficiency without paying any, extra money and change the design. See, that's why I say this type of knowledge is very, very important. Okay, so all right. So we will see the efficiency. Okay, we see this one. Okay, the ripple of the inductor current. And of course, the most important is the capacitor voltage, because this is the voltage of the output. This is what your load is seeing. Okay, this is what your load is seeing. Okay, so now we move on. All right. Okay, now for the buck converter, right, there is a thing called critical inductor. Now, critical inductor is the inductor value, the smallest value you can use for your design. Okay, that is the critical inductor. Now, the smallest value you can use to ensure that the buck converter will be operating in the what we call CCM, okay, continuous current mode. There's been as we know that we are using a chopping method, right? We turn on the transistor, it charge the inductor. We turn off the transistor, the inductor discharge. But we cannot turn off it too long because the energy in the inductor may not last that long, right? When we want to ensure that will continue, so there is a term called what we call buck converter critical inductor. Okay, the critical inductor can be calculated using this one. Okay, you can go to MATLAB. I have created these tools so that you can key in 12 volt and you can play around with the duty cycle. Okay, then it will show you, okay, the critical inductor. So this is a very important graph to tell you. All right, now, if I operating at 20 kilohertz of switching frequency, right, this is my critical inductor, the lowest inductor value I can use. All right, so it will give you the idea of what is the lower. You don't go below that. You go below that, then your what we call your buck converter will not operate in this CCM mode. It will operate in what we call DCM mode, discontinuous current, okay, mode. All right. So this is one of the very important factors to look into when you design this buck converter. So maybe let me see, run this one. You can download this program, okay, in the file exchange. Okay. Buck converter. Oh my goodness, where I put it? Wait, I also cannot find it. Critical inductance mode. Mana. Okay. So when you run this one, okay, you will have this. Okay, so you see, in fact, our duty cycle changed, right? You see, the line also changed. So that means you must choose an inductor that will work through the range of the duty cycle you are. Okay, if your output is fixed 5 watt, not going to change. You know that your duty cycle is, let's say, 0.5, then it's easier. Okay, you can know, what is your the inductor, whether it's suitable or not. Okay. So you can actually see that when your duty cycle change, okay, this L critical will change as well. We will try to match it around the area here, around the area here. So this is what we call, okay, the critical, okay, inductor. Now, what is the difference when you operate in CCM and operate in DCM? That's the difference here. Okay, if you find the critical inductor, the smallest value you can do, right? And you will see that. Okay, you see, this is the inductor current, right? This is the switching. So the charge, discharge, charge, discharge. When it touches 0, right? Okay, it will charge again. That means your current to the load is continuous. So that's why it's called CCM, continuous current mode. Your current won't break. Okay, but if you choose a inductor that is lesser than the critical inductance, this is what happened. It got charged, okay, and it discharged until 0, it stopped, right? That means at this time, there is no current, supplying to your load. Okay, your inductor are too small, in other words. Okay, your current are too small. So in this operation mode, we call DCM. So it will cause instability to your stability, current supply, okay, to your load. Okay, so that's the difference. Okay, to solve this problem, you either change the duty cycle, you change the switching frequency, or you change the inductor to a higher value. The smallest is ngam when the discharge touches the 0. But the one we design, right, is way higher than the what we call this the CCM. So you see, no worry. You see the current is, you see the 0 is here. The inductor charge, the discharge will not go until 0. So this is the good design. You ensure that your load will still have current continuous. You see, when the discharge is the time, you see, the time when the transistor turn off, right, is the discharge time. Okay, the time when the transistor turn on, right, okay, is the charging time. Okay, so when you design whatever you do this, you design, you get this value. Okay, they say, oh, this value you either straight away put into a simulation and run and see it for yourself. Or when you get this value, you quickly can use this method, this equation, to verify your critical inductance. Is it okay? Is it, if the critical inductance, okay, let's say you are having like this one, how many? 1, 2, 3, 4, 5, 6, 150 micro. Okay, the microhenry. Okay, the critical inductance 100 microhenry for this one. And our design is 360, so it's higher than 150, right? So that means this inductor is safe to use. If suddenly your design, you get an inductor that is lesser than the critical inductor, which is, in this case, is 150 micro. Let's say you design for some reason, you end up with 100. Now 100 means it is lesser than the critical inductor. So when you lesser, what happens is that, I say, you will end up like this one. Okay, you won't have a continuous supply of current. So that is the one of the case you need to look into when you come to DC-DC converter. All right. Okay, understand this one? Any questions?
No questions.
Okay, good. Because we will see this again in post and all. So this one is important that you have to aware. So you see everything, converter, like I said, your switching frequency, your voltage drop, okay, and all this critical value you have to understand in order to design a good converter. Buck converter are widely used in computer power supply. Okay, our computer, laptop, and desktop power supply. Okay. Okay, come to gain. Okay, the good thing is that the buck converter gain is a linear gain. Your gain is equal to your D. Okay, because your D is just a V out. Okay, divided by V in, right? So it's a linear function. Okay, it's a linear function. The linear function in the sense you can see that the x-axis is duty cycle, the y-axis is the power output. Okay, or the voltage output. So your duty cycle is 1, you get 1. Your duty cycle is 0.5, you get 0.5. So it's a linear function. But of course, in practice, is theory only. Okay, in theoretical, as we know that it won't be happen, right? When we did that one, because of the voltage drop, all this and that, you may need to have slightly higher, a little bit of 0.55 to get 0.5 output. But again, what doesn't change is that it is a linear function. Okay, so another thing important to this buck converter is that we call the input impedance. Okay, so this is a buck converter. And the buck converter will be connected to a load, right? A resistor load, for example. Okay, a resistor load here. The input resistance means that the source, okay, the DC source that look into the buck converter by right, let's say in our example, right, we have a 5 ohm here. Your source should see 5 ohm, right? But in buck converter or DC converter, it is actually depend on your duty cycle. Now you can see the R in, the input impedance. That means what the source see is actually depend on your load resistance divided by your duty cycle. Okay, divided by your duty cycle. That is what your load seeing your buck converter input impedance. That means you have a 5 ohm here, but what your source see here is not necessarily 5 ohm. Okay, it's divided by, let's say, 0.5. Okay, then you will actually see 10 ohm here. But your load is 5 ohm. But the buck converter act as a conversion, not just to convert the power, not just to bring down the voltage, but at the same time, it changes its input impedance to fit the source. Now, for normal battery operation, this is not important. But the important one is if your input is a solar PV panel. That is important because of solar PV is not a linear source. So it will look into, by changing the impedance here, right? You can actually use this method, okay, to track the maximum power of the PV inverter, of the PV panel, sorry. And of course, I also did the graph to show that, okay, the duty cycle and the input impedance. Okay, so the top one is almost infinite already, like you go all the way up. Okay, so you can see that this is the graph, is an inverse. Okay, it's an inverse, what we call exponential. Okay, so that's mean for the gain is a linear. For the input impedance, okay, it's an inverse exponential. Under normal, what we call operation doesn't really important, but it's important when you design a solar charge controller where there are MPPT, maximum power point tracker. Okay, this will be very, very important to make sure that you can track the maximum power, okay, that deliver by this, by changing, okay, the input impedance of the buck converter. Okay. Okay, so any question up to this point? Okay, so I don't think I have time to demo this already. Okay, because to demo this input impedance, right, I need to show you how MPPT works. All right, but I don't think we have time for this. So, but as long as you know this is important in future, if you do any FYP that related to this, it is easier for you to understand when you refer back my notes here. Okay, I will skip this tutorial. So this tutorial is just a sample of how your final exam will look like. Okay, so like, I want to have input of 12 volt, 5 volt output, and let's say I have, but my inductor is 100 and capacitor, okay. Now I give you the value and you determine the ripple in percentage, okay. And show the voltage in percentage. That means you actually using this equation, okay. And I want you to find this, find this one. So you just make, algebra, right? You just put L this in, take this out. You should be able to find this, how many percent. So this equation is just now you can play around to what you want to find, okay. So this is just some sample examples, okay. Color and illustrate is waveform indicating, okay, this one in exam you need to draw, okay, so it is something like that you need to draw like this one, okay, just draw, then explain, charge discharge, what we call the percentage. If it's Simulink, then you use Simulink. I'm not sure by then we are going to do online final exam again or on the physical. I can't tell. Okay, but this is something you all should know how to do, as I already showed in the class here. Okay, so now, all right, tutorial. Okay, now, then of course I will ask you, under this condition, is the buck converter is operating in continuous current mode or discontinuous current mode? Okay, then if, let's say if you know is that, then briefly explain. Okay, my exam, right, explanation, I do not need to have a very detailed, very lengthy, full page of kind of explanation. It's just simple diagram, okay, a few statements, okay, that should do, all right? Because I don't encourage students to really memorize the answer and then write it back, like the karangan you all did in your SPM, all this. I mean, in the old days, I actually doing that, okay? I memorize the whole thing and kind of pop it out. It's not good because really you learn nothing at the end. You just, even you score A for that, it's meaningless. It's rather than what you really understand, come out from your mind and you write it down. Okay, of course I don't look into grammar mistake, all this in the paper like that. Spelling mistake is, of course, it has to be correct okay. Okay, so that will be the buck converter under open loop. That means you control the voltage output by controlling, okay, the duty cycle here. Okay, see, there's no feedback at all. You just control here, right? Now, the next one is what we call feedback control. Okay, feedback control, all right, buck converter feedback control. We have a power source with a buck converter, we have a load, and then we will have a feedback control, okay, to the buck control. Now, most of the commercial buck converter are in this manner. The good thing of feedback is that, like, remember just now when you want to find 5 watt, you had to try an error, right? Like our 0.41, 42, 43 until you get 5, because you are doing manual control. So, but if with feedback control, this is done automatically. So you just need to put in the reference voltage that you want this buck converter to output. That, okay, the control will do it for you. Okay, so now the buck converter topology you already know, very important. Okay, you have to remember how to draw it. And then of course now we move to the control part. Control, again, like I said, okay, it's a closed loop control. This is what you have learned in your control class, right? The plant will be your buck converter topology, right? Your topology, okay. That consists of the switching transistor, and of course the most important is the LC filter, okay, and of course the diode, okay, and of course the transistor switch. Okay, and then we have a feedback, okay, how many voltage you want, Okay, we have feedback sensor, come back here, reference. Okay, let's say you want to 5 watt, you set the reference 5 watt. You want it to 10 watt. Okay, then you set 10 watt. You want to 3.3 watt, you just set 3.3 watt. You want to be 1.5 watt like a DC normal battery, you just put 1.5 watt. And then the error will go to your control. Okay, the control is simply just a PI controller. Okay, PI controller. All right. Okay, so this will give you an overview, okay, of the control. And I will go through one by one how to model the plant, how to do the control strategy. All right. Now we look at the plant modeling. There are 3 ways of doing the plant modeling. First way is what we are doing now. We call detailed circuitry modeling. That's the most accurate but slow computation. That's when you draw the circuit, right? That's why I asked you all to do, because we are going to use this method. There are second method called average circuitry modeling. Okay, so average circuitry cannot model switching information. You will not know what is the switching loss, but advantage is fast computation. And the next method is called S-domain, which you all will already learn in your control, okay, system, right? The 1 over S plus 1 as a model. Yes, we can model the entire buck converter in this form. And I will show you how to do that, okay? So, okay, I think, oh, it's already 6:30. Okay, never mind. I think, okay, I think we will do that in the next class already. Like I said, make sure you get all this ready, because we are going to do feedback control in the next class. Okay, in the next class, and how to tune the PI. This will take some time. Make sure your model is ready, because otherwise it will take a longer time. And then for those, I'm not sure, when you all install MATLAB, right? You all install all, right? Or if you don't install all, make sure you install the what we call this model or plant identification model, or else you cannot run this one, because there is a PI controller tuning method I'm going to use, okay, to teach you all how to do this. Okay, you need to install the plant identification toolbox. For those who didn't install all, okay, otherwise you won't be able to run this in the next class. So I will show you how to identify the plant and how to design this and how to do this in X domain as well. Okay. And then I think next class, okay, good. Make sure you install Plex. We'll do a simple buck converter as well. And I will talk about how the battery charger is designed, okay, using these buck topologies, and how the real application as well. So, okay, next class we should be able to get this done. Okay, any questions?
Yeah, Dr. Rodney, when you say plant identification toolbox, you really mean system identification toolbox, right?
Yes, system identification, sorry, yes. Make sure you all have it. Otherwise, right? Otherwise, you won't be able to run this. Make sure you have the system. Yes, thank you, Ryan. System identification toolbox. Make sure you install this. This is required for this PI tuning purposes. Like I said, there are thousands of ways to do PI tuning. It depends on application. Like the DC AC, we just use the time constant, okay, divided by the inductor value. We will actually get the P and I value. But you cannot use that method for this DC-DC converter, all right? So we have another method of that. And then just make sure that you guys install Plex. I think I will spend a little bit of time at least, so that you will be thinking that Plex is a stranger, all right? Because Plex for small circuit, you won't see the difference, to be very honest, in between MATLAB. But when you're running a circuit at a longer time, you will see the difference, okay? Especially the assignment you all do, you will definitely see the difference. And then, okay, again, hey, your group assignment, still a lot of students. I think still half of the class didn't have a group. Please do it as soon as possible, all right? Because you are telling me that you guys still don't have group, that's why you won't be able to start or whatever, Okay. Now the knowledge you all require to do the grid inverter already teach. I even show the in the Simulink. Okay, now you just need to implement in Simulink. Okay, Plex may be too new to you. That's why I say maybe I spend a little bit of time to show you DC. I cannot show you DC AC lah. If I do that, I show you the answer already. So at least you will have familiarity with that. Okay, so like I said lah, for those who already know Simulink, I fully encourage you all to take part and do the Plex. So you will gain two different knowledge, because Plex is a very specializing software for Power E. Of course, other than Power E, you cannot do anything other than Power E lah. That's a disadvantage, I would say. Okay, and MATLAB, of course, is a very general software. You can do programming, very powerful as well, but it's not specializing, okay, on just Power E. So pro and cons lah. It really depends on your project work lah. Okay, and which one to use lah. And that's why I would just like to take this opportunity to let you all try and learn something new there lah. Okay, all right, 6:30 already. Yeah, hopefully by next week the case go down lah. Then we can go back to physical class. Otherwise, I also don't know lah. Okay, okay, see. Still get very, very strange value. Who else get the correct one? Ahmad. Okay, yeah, Ahmad get the correct one. Dae Boon Hong. Okay, wow, all 90%. Oh, because you all change this one. You can see you change the duty cycle, or you also actually indirectly change this efficiency. Efficiency is not constant, remember. It changes when your duty cycle changes as well. So when you do design, right, you have to make sure that you have to know, oh, my buck converter or the charger. The best example is your handphone charger. It's always work on 5 watt. You have to make sure at that duty cycle, you get the highest efficiency you can get. All right. Okay. Oops. What is this? System. Okay. Guys, you can refer to Ryan post here, system identifications toolbox. Make sure you install it in your MATLAB for those who didn't install. Otherwise, you won't be able to do the thing. Okay. Okay. Yeah, MATLAB need a long time. Never mind. We will see the big difference. I really looking forward for your report lah. You don't tell me, oh, MATLAB is slow, Plex is fast. Wow. You have to give me a much more, in-depth and critical analysis lah, by how many percent, for example, fast and slow. Okay, perhaps the strain because the display are long. It could be, I can't tell lah. So you just try to work it out lah. Okay. So yeah, I think 6:37 already. So any more questions?
I have one question, but it's not really related to buck converters.
Okay, why is that?
Yeah, you see this one is still pulsating like because of the ripple current. So could we really call this a DC AC converter before the?
Yes, we still call it DC. Yes, because the pulsating at the DC is actually very low already.
Low.
If you use 2%, 1% is very low already. You see, AC means what? It will change from positive to go to 0 and go to negative cycle, right?
Oh.
Yeah, that is called AC alternating.
That's the definition. Must go to negative cycle. They only consider AC.
You have to go all the way from positive to negative cycle. We call it AC. But this one, even they got oscillate, but it's still in AC, right? It oscillates from, for example, 5.1 watt to 4.9 watt. It oscillates here. It's still DC. Because the polarity is alternating current. You know the word alternating.
So the alternating part is the polarity.
Yes. That is what happened in our AC plug.
I see. That all makes sense now. Okay.
Yeah. Okay. No, you see, I tell you what, even up to today, the power supply, whatever we use, okay, is not 100% so-called flat. It will have some form of oscillation, but very low, like 1% or 0.1% of 5 volt. That is, unless you use a scope and you zoom until you can. I mean, you can try it on your buck converter here. You increase the capacitor for 25 microfarad, maybe to 250. Blindly lah, of course, you will see that it's almost smooth already. I will demonstrate this in a boost converter exercise. Maybe I try this one first. See can or not. Yeah. Okay, wait.
Okay, thank you. No more questions.
Yeah, this one I don't have scope. So wait, I'm trying to actually show you if this thing works, because now I am not design it properly, just simply put a value just to, yeah. It's normal, Ryan. You are not the first one who always confuse between AC and DC. Because you see, AC, right, is what we call, it generated by the generator. So the generator has to alternate, go through the negative cycle. That is how we get the AC. Okay, so now I think it's quite flat already. Let me just change the time to a longer time. And then, I haven't shared screen. Wait. See, I got so excited until I forget to share screen. Okay, now let me just share screen again. Now you see, I just simply change this one to a very high value here, 4 watt something now. You can see the DC is almost like real DC already, you know. Ryan? You see, I zoom in, I even cannot see any fluctuation. You see? Okay, I do this for a purpose lah, so that you will know that, if you don't design properly, you will see some oscillation, you know. I mean, that is what, we are paying for, you know. You buy a handphone, you buy a charger, this is the design. Of course, they will have much more complex design using flyback, which I am going to show you all at the end of the DC-DC converter lah. So, okay, did I answer your question, Ryan?
Yeah, very satisfyingly.
Okay, thank you. Okay, so yeah, I think yeah, it is, yeah. Okay, I think I catch back the time when I wait just now. Okay, like I said, good. Thank you for all your attention. Please get your Plex all installed, system identification installed, so that we make our next class on Thursday much more smooth. All right. Okay. So if no questions, all right, we will end the class today.